Good morning, everybody. I welcome you all to this series of lectures on microprocessors and microcontrollers. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today I am going to discuss about the instruction set of 8051 microcontroller. So these various instructions of 8051 microcontroller, they can be addressed by using different modes. The different addressing modes are immediate addressing mode, direct addressing mode, register addressing mode, register indirect addressing mode, relative addressing mode, absolute addressing mode, long addressing mode, and indexed addressing modes. These are the various addressing modes using which the various instructions of 8051 microcontroller are accessed. So 8051, it has 255 instructions, and there is 8-bit opcode which is used for these instructions. So when you use 8-bit opcode, the opcode is going to range from 00 to FF. And mainly the instructions are grouped under 5 categories: arithmetic instructions, logic instructions, data transfer instructions, Boolean instructions, and branching instructions. So these are the 5 groups of instructions. First, let us discuss about the arithmetic instructions. Add is one of the instruction, and add C is also the instruction for addition, which involves the carry bit. So add instruction, it is used for 8-bit addition between the accumulator and the next operand, and the result is always directed to the accumulator. And depending upon the result, the carry flag is activated or deactivated appropriately. And add C instruction, here the carry bit also is included in the addition operation, and accordingly the carry flag is set or reset appropriately. For example, let us see this addition of add 1E44256CAH. Okay, so this is for the 16-bit addition. Okay, so clear C. First, let us clear the carry flag. Then move A 44H. So 44H is moved to the accumulator, and add A CA. So C, the next byte is added with the higher byte is added with the we have to add 1E44 with 56CA. So 44 is moved to the accumulator. Then the lower byte of the second operand is added with the contents of accumulator, and the result of addition 44 and CA is stored into R1 register. Next, 1E is moved to the accumulator. It is added with 56H, and it is added with R2. So the result of the addition is 75H. So the overall result 750EH is stored in R2 and R1. Now DA is a decimal adjust the accumulator. The format the accumulator into a proper 2-digit packed BCD number, and it operates only on the accumulator, and it works only after the add instruction. So after addition, when you get the result in hexadecimal format, to get a meaningful result in decimal format, decimal adjust accumulator is used. This I will explain you with an example. And next is subtract borrow. Subtract with borrow. So here the subtract the operand with the previous value of the borrow flag from the accumulator, and the result is stored in the accumulator, and the carry flag is set or reset appropriately. Now let us see the example for the decimal adjust accumulator. So when you add, let us say add 34249. So first clear C, clear the carry flag, then move A 34H, then add A 49H. So this is when you add 34, with 49, what you get? You get 70. 70 is in hex format and that is not meaningful. Suppose you do the same thing with decimal addition, what you get? You get 9, 4, 13, 437, 83 you get. So this is meaningful. So to get 83, what we have to do is we have to do the decimal adjust accumulator. So correspondingly, the contents of accumulator are adjusted to the value 83. How it is done? So this 70, because this is more than 9, 6 is added to this. So what is d plus 6? D is 13 and this is 16, 19. So this is, you get here 3 and 1, so 8. So like that, the contents of accumulator are adjusted to 83H. The next part of arithmetic instructions are increment, decrement, multiply AB and division AB. So increment, it increments the operand by 1. So the operand can be a register, a direct address, indirect address, or a data pointer. And in decrement, the operand is decremented by 1. And the operand can be a register or the direct address or indirect address. And similarly, let us see the multiplication, mul AB. So multiply A with B and place the result in AB. So when you do this multiplication, the contents of A are multiplied with the contents of B, and the higher byte is of the result is stored in B, and the lower byte is stored in A. So this is how the multiplication operation is done. And as far as the division operation is considered, so divide A by B, so A by B, and the quotient is stored in A, and the remainder is stored in B. So this is how the division operation is done. Next we have the logical operators. In logical operations, we have the ANL or ORL, and they work on the byte-sized operands or the carry flag. For example, ANL, A, RN. So you store one byte in A and another byte in one of the registers. We have 8 registers: R0, R1, R2, R3, R4, R5, and R6 and R7. So another operand is stored in one of these 8 registers, and logical AND operation is done between the contents of A and the register, and the result is stored in A. And for ANL, A and direct, so here one of the operand is stored in the memory. So the address is specified as a part of the instructions. So direct, so this comes under the direct addressing. Okay, and the result is stored in the accumulator. Next, ANL A @RA. So what is it? This is indirect addressing. So here, the next operand is stored in the memory, at the address specified in the register RA, and the contents are logically ended with the contents of accumulator, and the result is stored in the accumulator. And the next instruction, this one, comes under the category of immediate addressing. So ANL A, immediate data. So the data which is given in the instruction is ended with the contents of accumulator, and the result is stored in the accumulator. And ANL direct A. So these are all here, only the destination source are interchanged. Then ANL C bit. So the carry flag is ended with the bit, and the result is stored in the carry flag. Now XRL. XRL is exclusive OR operation, and it works on bytes only. And CPL and CLR. CPL is complement, CLR is clear. So complement and clear. So they work on the accumulator or the bits. For example, CLR P1.2. So there are 4 ports in 8051: P0, P1, P2, P3, and the contents and these are all 8-bit ports. So the third bit of port 1 is cleared. That means it is made 0 when you execute this instruction. RL, RLC, RR, and RRC. So these are for rotating the contents of the accumulator. RL and RR, they rotate the contents without the carry, whereas RLC and RRC, they rotate the contents along with through the carry. So that means the carry bit comes to the most significant bit or the lowest significant bit depending upon the rotation. Then swap A. Swap A is swapping the upper and lower limits of accumulator. So for example, before execution, after execution, let us say the contents of A are 49. So when you do swap A, after execution, it becomes 94. So that is how the instruction is executed. Okay. Next is there is no compare instruction, but it is built into the conditional branching instructions in 8051 microcontroller. Now let us come to the data transfer instructions. In data transfer instructions, we have move, destination, and source. It allows data to be transferred between any two internal RAM or SFR locations. SFR is special function register. And stack operations, pushing and popping the data, are also internal data transfer instructions. For stack purposes, the internal RAM is used, the general purpose RAM, which is 80 bytes, is used for stack operations. And pushing increments the stack pointer before writing the data, whereas popping from the stack, it reads the data and it then decrements the stack pointer. And 8051 stack is kept in the internal RAM, and 8-bit data transfer for internal RAM and the SFR. See, we have 128 bytes which are allocated for the internal RAM, internal data memory. So out of this 128 bytes, 32 bytes are for the register banks, 16 bytes are the bit addressable memory, and 80 bytes are for the general purpose RAM. This is the distribution. So 8051 for stack purposes, we use this general purpose RAM. Okay. So 8051 stack is kept in internal RAM and 8-bit data transfer for internal RAM and the SFR. So move RN data. So this data is transferred to the register. Move A @RA. So this is the indirect form of addressing, which we have already discussed. And the contents of the memory whose address is specified in R1 is transferred to the accumulator. And move RN direct. So here the address is specified very clearly as a part of the instruction from the contents of the address which is specified here is moved to the register RN. And similarly other instructions move direct and move direct data. So here the immediate data is transferred to the memory location internal RAM and move @RA direct. So these are all the instructions which are used for the data transfer. So here now let us see for 1-bit transfer involving the carry bit, move C bit or move bit C. And for 16-bit data transfer involving the DPTR, we use this move DPTR move DPTR immediate data. DPTR is data point register, which is a 16-bit register. So move DPTR hash data. So this data has to be 2 bytes. and move code byte. So how you do? Load the accumulator with the byte from the program memory or move use indexed addressing. So if you want to move the code from the program memory, you use this instruction move C A plus PC. So this is the PC is a program counter which has a 2-byte address. To that that contains the base address. To that you add the offset address which is there in the accumulator, and from the effective address and the contents of the memory location, that effective address is moved to the accumulator. And this is here the effective address is formed using the contents of DPTR. DPTR is data pointer. Next, MOVX. So MOVX is used for data transfer between the accumulator and a byte from external data memory. So X is external data memory. So move A at the rate MOVX A at the rate DPTR. So here the data memory is outside. So the contents of the memory location which is given by the DPTR is transferred to the accumulator. Okay, so like that this data is moved or managed. Next, push and pop, these instructions are used for stack related things. So push and pop a data byte onto the stack. So the data byte is identified by the direct address using the internal RAM locations. Push DPL pop 40H. So XCH is exchange the accumulator with a byte variable. So XCH ARN. So you exchange the contents of the register and the accumulator. So whatever is there in accumulator goes to the register, and whatever is there in register it goes to the accumulator. For example, before execution, okay. So when you execute this instruction XCH AR1, then what happens? 2F goes to the accumulator and 42 comes to the R1 register. So this is how the operation is performed. And XCHD, so exchange the lower digit of accumulator with the lower digit of the memory location specified. So the higher nibble is not touched. So that is for exchanging the lower digit of the accumulator with the lower digit of the memory location specified. That means the lower 4 bits of the accumulator are exchanged with the lower 4 bits of the internal memory location identified indirectly by the indexed register. So the upper 4 bits are not changed. Next, let us come to the Boolean operations. So Boolean operations, we use only the single bits. So all bit addresses, they use the direct addressing, and bits may be made 1 or 0 depending upon the instruction set or clear. So this group of instructions is associated with the single bit operations of 8051. So the P, OV, AC. P is the parity flag, OV is the overflow flag, and AC is the auxiliary carry flag, cannot be directly altered. So this group includes set, clear, complement, or move, and you can also use the conditional jumps. For example, clear. So clear P1.1. So clear the second bit of the port 1. Similarly, clear C, clear the carry flag. Set B A2. So or set B C. So here the accumulator, the third bit is made as 1, and here the carry flag is made as 1. CPL 40H. So complement the bit or the carry flag. So CPL 40H complement bit 40 of the bit addressable memory. So that particular one bit only is complemented. Next, other Boolean operations are ORL, ANL. ORL is for ORing, and ANL is for ending. Suppose if you say ORL C20H, so OR bit 20 of the bit addressable memory. Similarly, ANL C complement 3, 4 each. So you take the bit 34 of the bit addressable memory, then complement it, and with that you add the carry flag. So the next Boolean operations are used along with the jump conditional jumps, jump carry or jump no carry. So jump to your relative address, carry flag is set or cleared. Similarly, jump below, jump no below. There is the jump to your relative address, the bit is set or cleared. And JDC, jump to your relative address if a bit is set or clear the bit. And coming to the branching instructions, the 807 provides 4 different types of unconditional jump instructions: short jump and long jump. For short jump, we use 8-bit signed offset. So when you use 8-bit signed offset, what is the range of jump you get? Minus 128 bytes to plus 127 bytes. So this is the range you will get. And in long jump, we use 16-bit address. So obviously these are 3-byte instructions. So these are capable for referencing any location in the entire spectrum of 64 kilobytes of program memory. Now in absolute jump, we use the 11-bit address. So what happens to the remaining 5 bits address? Remaining 5 bits are taken from the program counter. So they are not modified. Only 11 bits are taken from the instruction, and accordingly the branching is done. So when you use 11 bits, what is the range of branching you get? 11 bits means 2 power 11, so that is equal to 2 into 2 power 10, so that is equal to 2k. So the location must be referenced within 2 kilobyte memory page containing the A jump instruction. And this is the indirect jump. So jump is done to the address, and the effective address is formed by adding the contents of accumulator with the contents of the data pointer, and to that the jump is done. So 8051 provides 2 different forms for the call instruction. Similarly, absolute call and the long call. In absolute call, like A jump, here also we use 11 bits. So the subroutine must be within the same 2 kilobytes piece. And in long call, we use a 16-bit address similar to L jump, and the subroutine can be anywhere in the 64 kilobytes of memory space. So both these forms, both forms push the 16-bit address in the next instruction of the stack and update the stack pointer. And 8051 provides 2 forms of the return instruction. One is returning from the subroutine, and another is returning from the interrupt. So when we return from the subroutine, pop the return address from the stack and continue the execution from there. But when you return from the interrupt service vector, ISV is the interrupt service vector. ISV is the interrupt service vector. So pop the return address from the stack and then restore the interrupt logic to accept additional interrupts at the same priority level as one just processed, and then continue the execution at the address retrieved from the stack. And PSW, which is the flag register, that is not automatically restored. And 8051 provides 5 different forms of conditional jump instructions. In conditional jump instructions, you get only the branching in the range plus 120, minus 128 bytes to plus 127 bytes. That is only the range. Minus 128 bytes to plus 127 bytes. So all conditional jump instructions, they use 8-bit signed offset. So that is why you get the branching in the range minus 128 bytes to plus 127 bytes. So jump on 0 is JZ or J no 0. So jump if A is equal to 0 and jump no 0 means jump if A is not equal to 0. So the check is done at the time of the instruction execution. Similarly, jump on carry or jump on no carry. So jump if the carry flag is set or cleared accordingly. If JC means jump if the carry flag is set. Jump no carry means jump only if the carry flag is 0 or not cleared. And jump on bit, JB or jump no bit. So jump if the specified bit is set or cleared accordingly. And the addressable bit can be specified. Compare and jump. Okay, so that is C and GA. So compare the magnitude of the two operands and jump if they are not equal. So that is the meaning of this instruction. So CJNE, compare, jump, not equal. If they are not equal, then only you do the jump. The format is like this: compare, jump. So one operand is here, and another operand is at the address specified by this second operand. And if they are not equal, jump to this label, relative address. And this is compare a data. So this is a sort of immediate addressing. So the contents of accumulator are compared to the data, and if they are not equal, then the branching is done here. Similarly, compare, jump, not equal RN. So the contents of register are compared with the immediate data, and then the branching is done if they are not equal. And this is the indirect form of addressing. So the comparison is done when one of the operand is stored at the address given in the register, and it is compared with the data which is given as a part of the instruction. If they are not equal, then the branching is done. Next, decrement and jump. So decrement and jump, the instruction is D and Z. So decrement the first operand by 1, and if it is not 0, then jump to the location specified by the second operand. So decrement, jump, Rn 0. So Rn, the contents are decremented by 1, and if Rn contents are not becoming 0, then it is control is transferred to this label. Similarly, decrement, jump, no 0, direct, relative. So the contents of the data or the operand which is whose address is specified in direct, so they are decremented, and if it is not 0, then it is control is transferred to the location given by this REL. No operation is NOP. Now coming to the stacks in 8051, so the register which is used to access the stack is called the stack pointer. So the stack pointer in 8051, it is 8 bits wide. So which means that it can take the values from 00 to FF. So when 8051 is powered on, the stack pointer is initialized with 07H. Or when powered on, or when reset is pressed, SP is initialized with 07H. Now you see here, move R6 25H. So R6 I am moving 25 data to R6, then move 12 to R1, then move F3 to R4. Now push R6. So when I am pushing R6, the contents of R6, which is 25, is moved to the accumulator. So 25 is moved here, and the stack pointer is initialized with 08. Now when I am doing push R1, then stack pointer is becoming 09, and R1 data is 12, that is moved to the stack. So similarly, when I am pushing R4, what is R4 value? R4 contains F3H. So F3H is moved to the stack and SP is initialized with 0AH. So these are all the various instructions of which are used in 8051 microcontroller. So we have a total of 255 instructions, and there is 8 bits which are meant for the opcode, and so we can use the opcodes. They lie in the range 00 to FF, and the instructions are grouped into 5 categories: arithmetic, logic, data transfer, and Boolean and branching. And arithmetic and logic operations we have discussed: add, subtract, add with carry, and if you want to see the result in a meaningful way, then we have to use the decimal adjust accumulator. And increment, decrement, multiplication, division, these are all part of the arithmetic instructions. Logical operations, you have AND, OR, exclusive OR, etc. And for data transfer instructions, we use the move. So you can move the data from the destination to the source. Both can be registers, or both, one of them can be memory, but both cannot be external memory locations. And this exchange and XD. Exchange is exchanging the contents of the two operands. And we have the instructions for Boolean operations. Similarly, we have instructions for the branching, conditional branching and unconditional branching. Similarly, we have instructions for the call, the calling the subroutines. So you have different ranges: long range and short range and absolute range. In long range, we have branching in 64 kilobyte spectrum. In absolute branching, you can have the range within 2 kilobytes of space, and in short jump, you can have branching from minus 128 bytes to plus 127 bytes. So with this, we conclude today's session on the instruction set of 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.